Okay.
Fantastic. Let's go. Maybe in case that wasn't clear, the kind of picture we had. So there's also we had X and X check, which were supposedly mirror Claviers, and then there should be this this correspondence between the Hodge diamonds, and then what I was telling you about is a more refined correspondence where if you take the vertical of the Hodge diamond on one side, that should correspond to the horizontal of the Hodge diamond on the other side. And I'm claiming that there should be like this nice correspondence where if you start with a point on one side, you tropicalize it, it's still a point. The fiber over it is S1 to the n, so it's a SYZ fiber. If you do it with curve, you tropicalize it, you still have curves. On the other side, you have the cycles that give you canonical coordinates. And now we want to like go up one more. All right. So now I'm switching my focus to toric Calabi-Yau freeze, but really I'm doing KP2 for now. We can do something more general later. And at the first step, I wanna argue to reduce to P2, E, where E is a smooth elliptic curve. And I'm going to use Pierre's talk from yesterday. So using Argus, Alexeyev, Bousseau. So in Pierre's talk, we had two sides. One side was, so the left side, that's the side where you have the canonical singularity. And then the other side is the side where you have surfaces. So the canonical singularity was, I think, was denoted by X. And then here we have the surfaces, but not just surfaces. They were surfaces, divisor, and line bundle. Okay, so I want to look at one special example, I think, which is also treated in their paper, which is what if the web with 5 branes, sorry, the web of 5 branes is the following. So I need to think about how I want to structure it. So the web of 5 branes is this one. So we have 2 minus 1, minus 1, 2, minus 1, minus 1. Now this gives you a toric surface. So, yeah, which is P2 quotient out by mu3, so the same as I had yesterday, and then toric divisor, and L is minus K. L is just minus K. And in particular, we have what does this look like? So the image to have is well, okay. First, we could have a refinement. Let me try. Yeah, we have on the other side that corresponds to, this is dual to some polytope, which is this polytope. Okay, and then that defines the canonical singularity, which is, so you take the cone, so you take the cone over this, so as empiric stock, right? So we had, so the cone over P, this gives us C3 quotient out by also mu3, or Z, maybe I should write Z, it doesn't matter, mu3. So here, mu3 acts with weights 1, 1, 1, and then here, well, here we have lambda times x is x, lambda times y is lambda square y, lambda times z is lambda square z. So lambda, yeah, well, so the weights are 0, 1, 2. The other weights are 1, 1, 1. So weights 1, 1, 1. Now, if you want to compute what this is, you can look at the dual polytope. So yeah, I'm going to be jumping a bit between the boards. I hope I'm not messing up your talk, Pierrick, but I think that's okay. So we have we have the dual polytope. So dual polytope to this is CP, the cone over P, to CP. The dual is going to be another cone, which is going to, I think it's going to be this one. It's going to look like this. So the dual is going to be, this is going to be the cone over this polytope. And then if you, you can describe this. So this you can describe as, it's the upper convex hull of and some piecewise linear function, and I think the values of it is determined by phi 0, 0 is 0. Maybe I put it here. So phi of 0, 0 should be 0. Phi of 2 minus 1 should be 1. Phi of minus 1, 2 is also 1. And phi of minus 1 is also 1. So I think this is correct. Yeah, fantastic, thanks. So we start with this subdivision. So this is a subdivision. This is a fan. Well, it's a fan we had over there. And then we introduce a piecewise affine function. We lift this to height 1, and we take the cone over it, which is the same as this one. Yeah, because here 0, 0, right? And now what you can see is, from this description, is you can see local coordinates. We can see that we have local coordinates are given by toric geometry. Namely, we'll have, if we take this picture, we'll have something. Now I can look at, I can take some local coordinate here, some local coordinate here. If I call this x and y, and then we'll have x times y is going to be t to some k, where k is the kink of phi along, let's call this rho, along rho. Yeah? So this is just toric geometry. So if you can do something like this, yeah? Yeah? Maybe the kink is free, I'm not sure. Okay? Very good. Let's go back to our picture. So the next step, the next thing we're going to do is we will subdivide. So we're going to subdivide this. Here you don't have a lot of choice. In fact, this is a case of a toric Delpezzo surface. You have a reflexive polytope. The kind of very natural subdivision is this star subdivision. I don't know if this has maybe it was called P bar. I don't remember. And now this will mean that we're adding. Now it's time for colors. So at the first step for the subdivision, so we added these. So here, it means we're adding an extra ray because we subdivide this, yeah? And then that gives us the resolution of this, which becomes Kp2. And then we have, I mean, this description with local coordinates. So this is still locally okay for Kp2. The polytope becomes, so the way the polytope changes is you're kind of cutting off here. We're cutting this off. And then you only have something like this. And you still, so this is going to be the polytope. And you still have like locally, you can still get local equations by very much doing the same thing as you do here. Okay? It would maybe takes a bit of time to just do it on your own, but maybe I won't do that. All right. So that was the first step. Now also the subdivision corresponded to here we did a we did we had a degeneration of our surface determined by this. So here, this one is the asymptotic 5-brane, web of 5 branes, 5 branes, and this one is just the web of 5 branes we choose. Right? So this corresponded to some degeneration. Okay. Comments? Is okay? Yeah, very good. So I also want to we have some geometry here. So the geometry, so Pierre explained to us that we need to look at the complement. So for now, the complement here is gonna. Well, sorry. First of all, let me give you a kind of picture. No, that's wrong. Let me give you a picture of what the variety looks like. So we have these singularities, something like this, and okay, something like this. I'm just trying to write my weighted P2 as a, so it has these singularities. This is weighted P2, yeah. So this is the, maybe I'll try to do it a bit bigger. This is a weighted P2. So this is, yeah. And then we have this there's this curve inside, which really is a thickening of this picture here. So it looks like this. And then, okay. We need to take the, right, in the toric case, we really take the complement. We take, so u, which is y minus d, which is just c star squared. And then what, yeah, and so there's also the, right, we also had this z, which was uv equals f. So this inside C2 cross C star squared, and here f xy, we can choose it to be 1 plus x plus y plus 1 over xy. Do you add a 1 or not? Yes. Maybe, yeah. So we have, and then each of these corresponds to a vertex of the Newton polytope. So this one here, right, this is, so this point here is 1, 0. So that this, so if I write z 1, 0 to be x, z 0, 1 to be y, then z minus 1 is 1 over xy, and z 0, 0 is 1. So this is really the Newton polytope of that f. Okay?
So you just write it out recipe for the mirror.
That's right. So yeah, I'm just copying what Pierre did yesterday. I'm cheating. I'm using his notes and plugging it in. But I should emphasize that what we're doing here is we start with the mirror and we go to the other side. But we want to do it the other way around. So which is what I'll get to towards the end. But I just want to, so here I want to justify that I'm allowed to replace KP2 by some log geometry. That's my goal. Okay. Very good. And then if you do this, then so fx. If I just write fxy, so this gives me some pencil. And in fact, it's if I look at the fibers of f. This is we saw this yesterday already. See yesterday.
Pencil of curves.
That's right. Pencil of curves. And maybe I want to write it in the following way. So we had yesterday I wrote t to the x cubed. Sorry. I want to write it this way. Shadow equals to 1. Yeah. So I'm varying the fibers. It's a bit a different kind of coordinate than that one, but okay. Very good. Questions, comments? All right. So at this point we have just the toric picture. We have a toric surface. We take an asymptotic. So we have a web of 5 branes. We have an asymptotic web of 5 branes. We have this surface. We have a divisor. The line bundle, I told you before, is just the anti-canonical. On the mirror side, we have this canonical singularity, and we have this subdivision, which gives us a resolution. All right, fantastic. Now, the next step we're going to do is we're going to modify this. We're going to modify this by adding 7 branes, like Pierre did yesterday. So we're going to add one here, and add one here, and then add one here. Okay. So we saw in the talk that doing this on one side. Oh yeah, and sorry, and then he also we also saw that we have this conic vibration, right? So this is a conic vibration. We had this conic vibration where over one point here we had a, and then over a point here we had this one. Very good. Before we do the blow up, let me say something else. Which is the following. So I told you, so that we are interested in period integrals. So there's a dictionary. Between S3s in H3 of Z, between a basis of S3s and a basis of Lefschetz thimbles.
What is the C?
So. Oh yeah. So here. So this is a conic vibration. Yeah. So I'm a bit all over the place. Yeah. Yeah. So we have. So this is a surface. We remove the boundary. So if we remove the boundary, you have holes here, right? So, and then the conic vibration. So we have this sort of asymptotic pieces here, and then if you're over this point, your vibration is given as such. If you're over this point, your vibration is given as such, right? And moreover, there's a dictionary between S3s in Z, between like spheres in Z and Lefschetz thimbles. And the way it works is, so if I have a Lefschetz thimble here, so it starts from some singularity. So this is where this is nodal fiber of the pencil. So the pencil of elliptic curves at this point looks like this. So we have a maybe so we have we in our pencil there are places where these we have some vanishing cycle, and so this vanishing cycle gives a Lefschetz thimble. So they correspond to vanishing cycles. So I think we have 3 of them because this family has 3 nodal. This pencil has 3 nodal. 3 nodal fibers. So yesterday I put a T cubed. Now I'm not putting a T cubed. Yeah. Now if you can, so these you can lift them. So if you have one of these Lefschetz thimbles. So this is, by the way. So I learned this from paper by Hokwai. This is with. I think this one is Lau and Seng. I think. Not you, I think. I mean, but maybe this is not like this is maybe Anyways, you can read in their paper, enumerative meaning of mirror map. I think I learned it for today. And so what you do is the way you lift this is so you start with this Lefschetz thimble, and then you want to lift it to the vibration over one point, which is away from the pencil. You add a S1. Like you add one of these S1s here, and then over the boundary, where you are on the fiber, these shrink to a point, so you just add a point. Right? So you can see that if I take a path from here to here, this is going to shrink to this point. Or I mean, I can choose such a I can choose such a cycle, and then and then if you put this together, you get. So what you really have is you have this this disk, and then over each point you have an S1, and then as you go towards the end, to the boundary, this S1 shrinks to a point, and so this will give you an S3. And you can, and so you have a basis of Lefschetz thimbles, which are given by the number of nodal fibers, nodal curves. You have these Lefschetz thimbles that are traced out by vanishing cycles, and then you can lift them to some S3s. Yeah. So that's a justification for why. So that's a justification for why I want to. Sorry, that's a. So step one. Step one, reduce to. So step one, to reduce to Lefschetz thimbles. But there's also step two. Because I shouldn't just do something because it works. I should also kind of justify, and that's where we're going to put the 7 brains. Okay, questions so far? Comments? So we have this beautiful geometry, and now we're going to add in some 7 brains. So I'm going to add in the 7 brains, and we're going to kind of follow through what happens. And I'm really referring to their paper, so Pierre Culian, Valerie's paper. This is described I think as an example in the last section, maybe. Yeah. But okay, very good. Now we add in these 7 brains. So so add 7 brains here. This corresponds to these blow-ups. So we're gonna this is gonna close up, and we're gonna have this. We're gonna push this in. There's gonna be this blow-up. Pushing it in. So I do get really excited when I have a chance to draw things, but I'm not a good drawer yet. So so adding 7 brains. 7 brains. So we get these blow up. This corresponds to blow up base locus of elliptic fibration. So C, AAB. So I'm really following AAB here. Okay, so now we still need to modify U. So now U, because after we do these blow-ups, well, this is no longer C star squared, but we added these, we added 3 copies of C, right? C, C, C. So we pushed in these. If you remove this point here, you added 3 copies of C. So we changed the topology. Okay, and so now it becomes in particular. If you look at this dictionary, we close up the ends, right? So this is, we close it up. So the 7 brains close it. So here the 7 brains also close it, yeah? And so that changes a bit the vanishing cycles, right? Because now we have something a bit more, that you could, yes. Anyways, let's not talk about this. Very good. Now it also does something on the mirror side. So remember, on the canonical singularity side, we had this picture where we have some x over x bar over delta, and this was in the toric case. We had so as Pierre explained yesterday, we had in this picture you have a smoothing of 3 copies of some affine toric surface. So we smooth it to C star, right? And now what this introduction of 7 branes does, as Pierre explained, is it changes the complex structure. So this smoothing at the level of Kp2 becomes a smooth. So this turns into a smoothing of toric divisor of Kp2. Yeah. So in the toric X. This is a smoothing. So this map here is a smoothing of facet of toric divisor to C star squared. Yeah, so this is, you can, the way you have this map, so you have this map that Pierre introduced to the line, and then you can view this as a smoothing of the toric divisors of Kp2. So you have the toric divisor, you have one compact component, and then you have 3 other components, which are line bundles over P1s, and then you're smoothing them together. And then that smoothing is the same as when I introduced these coordinates earlier, we had these like local coordinates, which were x, y equals t to the some kink, which really are present. Like you really have this, you have this picture, and then you have some piecewise affine function on the pieces. And then you take the cone over it, and then the piecewise affine function will determine you the smoothing, right? So it's really you have this picture here. You add some phi, and then that phi is determined by L, and then that tells you what the smoothing should be. And locally you'll have equations like this. So if this is confusing, I'm sure we'll see it more in later talks. However, by adding in these focus-focus singularities, what you're doing is you're deforming this smoothing. So this gets deformed to a smoothing where of the following object. So this is also explained in the paper. So I'm too scared to touch this. So this smoothing gets deformed to a smoothing of P2 union L, where L is the total space of O minus 3 restricted to E. And E is smooth cubic. Yeah? So instead of having, here we have 1, 2, 3, 4 components, now it becomes just 2 components. Yeah. So we have this component, and then we have something which is just some line bundles, which is just defined on the divisor, and then those are the objects we're smoothing. Okay. Maybe this, yeah. There's a bit, yeah. We'll maybe future talks will make this clearer. You can also there's a place to see this on the other side, which is we're gonna like these focus singularities will be moved to something on the other side, to also some focus singularities. So here we put it here, here we put it here, here we put it here. Maybe I also want to think about pushing them inside with these Hanani-Witten moves. And so HW moves will move it inside, and then and so this made this is a smoothing of the toric divisor inside P2 to a smooth cubic. So smoothing of toric divisor in P2 to E. Okay. Maybe we still have these lines here. Okay, and so now I'm gonna. So the last statement that I'm gonna make is the following. So the general fiber of this, I think this is a statement Kirik made, is going to be mirror to U, right? And the general fiber of this is P2, comma E. Okay? So let me recap what we said. So now I'm running out of space. So okay, so I'm going to rewrite step 1, which is, and then I'm going to rephrase it using the insight we just got. So step 1. So reduce to Lefschetz thimbles. So CLT. Chan laut sein. Step 2. So these are Lefschetz thimbles in U. Step 2, U is mirror to P2, comma E. This is CAAB. So that's the statement I just had here. If I so U is going to be mirror to the general fiber, which is P2, comma E. Where we really did, by doing this, we did smooth out the corners. We smoothed out the divisors, yeah. So this suggests that So this suggests the following strategy. We apply intrinsic mirror symmetry to P2, E. I just erased the sun. It's too sad. So that, this implies we have canonical coordinates. And then find the right Lefschetz thimble integrate over it. So here, this is. I'm not going to give you the spoiler what this is. I need to make some caveats. So and also we're using also at this point that the genus zero Gromov-Witten theory of KP2 is equal.
So when you say reduce KP2 to P2E, you're just saying those are just 5, right?
Yep, that's right.
You're not saying that the two fields are the same.
Excellent question. That's so. In terms of Gromov-Witten theory, so maybe I'll write this as a comment. So in fact, so Gromov-Witten KP2 is equivalent to Gromov-Witten P2E, and this is results. So this has a long history. So there was like this started with Takahashi Nobuyoshi, Gartman. Then there was a paper with me and Graeber and Rudat. So this is all in the genus zero case. So genus zero. And then in all genus, this is a fantastic paper by Rousseau, Longting, sorry, you're at the end, Shuiguo, Honglu Fan, and Shuiguo. Yeah. So what I told you earlier was just based on mirror symmetry principles, based on their paper. We expect this equivalence, but actually you can make it correct. And maybe I should say that in higher genus.
From that, I mean, the one that you're talking was not clear why they should be there. I mean, this one is the fiber.
That's correct. Absolutely. It was not clear, however. Oh yeah. So it's an excellent point. So it was not clear, but do you believe this? If you believe this, then it becomes more clear because we reduced, right? So the first step is we reduce. So step one, we go from Z to U, right? So step one is instead of looking at S3s in Z, we look at Lefschetz thimbles in U, right? So from maybe I could write it this way. So S3 in Z becomes Lefschetz thimble in U, right? So that's the first step. So the period integrals are the same. Yeah? If you believe this, I understand you're a bit reluctant to believe because you're not part of that paper. So if you believe this, then so that's the first step. Now the next step is okay. When I told you about it, so the next step is this one, and for this you have to believe their paper, and then the final ingredient you need that their Gromov-Witten variants are the same. And maybe I should point out that so these excellent question. So for open invariants, you mean? That's all. Excellent. That I really wonder. That is one of my kind of long-standing questions. So I will I will, since you, so I like to ask this everyone I meet, and I never gotten any really good answers, which is, you know, what about categorical, you know, like KP2 versus, I mean, let's do Y versus Y, let's do this. So total space of KY versus Y comma D. I really wonder. I don't know. I think, okay.
Do you have something of one over dimension? KP1.
So, so the answer is in terms of this, yes. So this, this equivalence in genus 0. This is for all YD with just Y has to be smooth projective variety, and the only condition is that D is Neff. This one is just this one you have. This one is for. So there are extensions of this. So how does this work? This is Y. So GW of Y of KY. So equal GW of Y comma D plus GW of D. And this plus is not the plus you know, but I'm identifying all the yeah, maybe. So if you combine these two, you get this. However, if you go to higher dimensions, this statement becomes much more complicated. Whereas this statement is true in all dimensions. Now, the reason so this is much more complicated, but here, for genus 0, the periods only give genus 0, right? Only genus 0, so that's fine. Whereas here we have to do something much more complicated. Now, but does it make sense, the strategy? Yeah, okay. So then we want to find the right Lefschetz symbols, we want to integrate over it, and then we want to use these correspondences, and then pretend that we did something for KP2. And also I want to say that there's also like a link to Open GW, which was studied in some of your papers as well. So they're like, this shows up in the other paper where you're part of it. So yeah. So I also want to mention this. Yeah. So Chan Lung, Chan Lao. I think Chan Lao Lung, right? Yeah, okay. So yeah. So okay. I failed at my task of becoming more Swiss. So time-wise. So I will end here. So I hope the strategy is clear. Oh, sorry, there was one more thing that I wanted to say, which is now it's a trick question. Do we see the canonical coordinates when I write? Remember when I write this, do you see the canonical coordinates? So the answer is no. I always told you that intrinsic mirror symmetry gives you canonical coordinates. Why are they not here? That's a question to think about. I kind of want to blame these guys, but of course there's nothing to blame. Of course you don't see canonical coordinates at this point, because what they're doing is going from this side to this side. You're only going to see them if you go the other way around, which is why we really have to run the program. But alternatively, we could also take the approach with open convergent invariance that you did in your paper. Yeah, so maybe I end here.
Well, thanks for being on time.
Yeah.
Because you just
yeah.
borrow some time from yesterday, right?
That's right, yeah.